So hello students, in this video we are going to talk about another very important concepts of ionic equilibrium, that is salt solution and the properties of salt solution. We know that salts are neutralization product of acid and base, but when a salt is dissolved in water, it can produce a neutral solution, an acidic solution, or a basic solution depending upon the nature of salt. So salt can be neutral, salt can be acidic, salt can be basic. We are going to have a brief summary on the property of solution of salts. So on the basis of the formation of salt from acid and base, salts are divided into four categories. So salts are divided into four categories. One is salt of strong acid and strong base. Like sodium chloride, it is salt of NaOH, a strong base, and HCl is strong acid, K2SO4, etc. Salt of weak acid and strong base, like sodium acetate, like calcium carbonate, etc. The third is salt of strong acid and weak base. Salt of a strong acid and weak base, like ammonium chloride, HCl is a strong acid, ammonia is a weak base. Anilinium nitrate, aniline is a weak base and nitric acid is a strong acid. And then the last one, salt of weak acid, weak base, like ammonium acetate, ammonium fluoride, etc. To predict the nature of salt in solution, the first and the simplest approach which can be followed is that a stronger component of the salt governs the nature of solution. A stronger component of the salt governs the nature of solution. So in first category, both acid and base are strong, so no component governs the nature of solution and the salt is neutral in solution, means pH is 7 at 25 degrees Celsius. In second category, there is a strong base. So salt of this category is basic in nature. So salt like sodium acetate, calcium carbonate are all basic and their solution will be basic with pH greater than 7. So stronger component governs the nature of solution. Salt of a strong acid, weak base. Now acid is strong, so salt is acidic and therefore the solution of salt will produce acidic solution with pH less than 7. Now both acid and base are weak. We cannot predict the nature of salt of this category directly unless until we know the ionization constants of weak acid and weak base. So here we have two different cases. One, Ka greater than Kb, means ionization constant of acid is greater than ionization constant of base. In that case, acid is slightly stronger than base and therefore the solution will be acidic. But if Ka is less than Kb, base is slightly stronger than acid and therefore the solution will be basic. So that is the way we qualitatively predict the nature of salt solution. The next step is quantitative, how we determine how much acidic or basic will be a salt solution. For that purpose, we must know the hydrolysis reaction of salt. Salt hydrolyzes, reacts with water to produce either some excess of H plus or some excess of hydroxide ion, and that determines the nature of solution. When a salt dissolves in water, the weaker component of the salt hydrolyzes, and that produces either H plus or OH minus, which gives acidic or basic nature to the solution. So the key concept in the hydrolysis reaction is what? Weaker component hydrolyzes to produce H plus or OH minus. So weaker component of the salt hydrolyzes. In case of salt of first category, there will be no hydrolysis since there is no weaker component. In second category, component from acid will hydrolyze since acid is weak. In third category, component from base will hydrolyze since base is weak. In fourth category, both are weak, so both acidic and basic component will hydrolyze. Let us take one of the hydrolysis of salt of weak acid and strong base, how it works. Suppose, hydrolysis of salt of weak acid plus a strong base. So to understand this, let us take a case of sodium acetate. Sodium acetate is a salt of weak acid and a strong base. The moment we dissolve it in water, it first ionizes completely to produce acetate ion and sodium ion, and it is the acetate ion which will hydrolyze, weaker component of the salt hydrolyzes. So acetate ion will hydrolyze like this. This we call hydrolysis reaction. So acetate ion will take H plus from water, producing hydroxide ion. It is the formation of this hydroxide ion which makes the salt solution basic. For this hydrolysis reaction, we define an equilibrium constant Kh known as hydrolysis constant. So let us first derive this Kh. So this KH will be, it is nothing but Kc, so concentration of CH3COOH into concentration of hydroxide ion divided by concentration of CH3COO minus. Let us multiply it by H plus and divide it by H plus. Now this H plus into OH minus is nothing but Kw, ionic product of water, whereas this H plus into acetate ion divided by acetic acid is Ka, ionization constant of acetic acid. So it is nothing but Kw upon Ka. So this way we determine hydrolysis constant Kh, which is now Kw upon Ka. The next is, if C is the initial concentration of this acetate ion and if alpha is the degree of hydrolysis, then at equilibrium C into 1 minus alpha will be remaining and C alpha will be hydrolyzed to produce C alpha of acetic acid and hydroxide ion. So if we write the expression of KH in terms of C and alpha, it will be KH is equal to C alpha into C alpha divided by C into 1 minus alpha. So 1 C will cancel off to give C alpha square upon 1 minus alpha. Again, we work out the same approximation as we use in case of weak acid and weak base, that if alpha is very small, then KH will be equal to C alpha square upon 1. We are ignoring alpha in comparison to 1 for a while. So alpha will be root under KH into C. So from the given value of Ka, we first determine KH, then from given value of C, we find out an approximate value of alpha. And then we decide what to do in the next step. If alpha is less than 0.1, then alpha can be ignored in comparison to 1. In that circumstance, KH, the expression for equilibrium constant, how it will be? It will be concentration of hydroxide ion into concentration of acetic acid. Concentration of hydroxide ion into concentration of acetic acid divided by concentration of acetate ion. Since hydroxide ion and acetic acid concentrations are equal, so we can write the numerator is equal to concentration of hydroxide ion square divided by concentration of acetate ion C into 1 minus alpha. Since alpha is less than 0.1, it is being ignored in comparison to 1. So 1 minus alpha will be 1. So denominator will be only C. C into 1 minus alpha. So 1 minus alpha is now taken as 1. So it will be C. Therefore, the concentration of hydroxide ion will be equal to KH into C under root. So now KH and C both are known. Solving for hydroxide ion concentration and taking negative log of it, pOH is determined, and then we subtracted this pOH from 14 to obtain the pH of the salt solution. But what if the alpha is not negligible? So if alpha is greater than equal to 0.1, we cannot ignore alpha in comparison to 1. We cannot ignore. Therefore, what we'll have to do in that case, we'll have to solve the expression for KH. So solve KH is equal to C alpha square upon 1 minus alpha. C is given, KH is known, so it will be quadratic equation. Solve for root of quadratic equation alpha, and then concentration of hydroxide ion can be determined as C alpha. So let us work out a numerical problem that to know how this derivation and all works out. So suppose given that Ka ionization constant of a weak monobasic acid is 10 raised to the power minus 12 at 25 degrees Celsius. A 0.5 molar solution of weak acid is titrated using a 0.125 molar NaOH solution. Determine pH of the solution at the end point. To solve this problem, first we'll have to see the neutralization reaction. How the neutralization reaction is occurring during the titration. So weak monobasic acid can be assumed by the notation Ha being neutralized by sodium hydroxide. So the neutralization reaction is H2O plus Na plus A minus. Concentration of weak acid is 0.5 molar, but the concentration of base is 0.125 molar, and this concentration is 1/4 of acid concentration. So V volume of acid will require 4V volume of base to reach the end point. Since concentration is inversely proportional to volume, so if concentration of base is 1/4, the volume requirement of base will be 4 times the volume of acid. So at the end point, the total volume will be 5V. So concentration of this conjugate base of Ha will be 0.5 divided by 5. Since volume is V plus 4V 5 times, so concentration of salt will be 1/5 of the initial concentration of acid that is 0.1 molar. That is the first point where students usually makes mistakes. So manipulate the concentration properly to find out the concentration of conjugate at the end point. So concentration of A minus is 0.1 molar. Now this A minus will undergo hydrolysis. So this A minus will hydrolyze, giving HA plus HO minus, for which KH is KW upon Ka, 10 raised to the power minus 14 upon K is 10 raised to the power minus 12. So it will be 10 raised to the power minus 2. Now find out the approximate value of alpha. Approx alpha is root under KH upon C. So KH is 10 raised to the power minus 2 upon C is 0.1. So it is root under 0.1. So it is approximately 0.33, which is much greater than 0.1. So we can say that alpha is not negligible in this case. So we cannot ignore alpha in comparison to 1. So what we'll have to do? We'll have to solve the quadratic. So it is not negligible. So solve KH is equal to C alpha square upon 1 minus alpha. So KH, which is 10 raised to the power minus 2, is C alpha square. C is 0.1 alpha square upon 1 minus alpha. So 0.1 will cancel 0.1 here, minus 1 power, so minus 1 will be left. So it is 1 by 10. So quadratic equation is 10 alpha square plus alpha minus 1 is equal to 0. Once this quadratic equation is solved, alpha will be minus 1 plus root under b square 1 minus 4 into 10, 40 into minus 1 plus 40 divided by 2a, which is 20. So 41, root under 41. So root under 41 will be somewhere around 6 6 are 36. So around 6.5. So around 6.5, 6.4. So it is around 6.5. I am taking 6.5. So sorry, 6.5 minus 1, 5.5 upon 20. So it is 5 4 are 20 and 1.1. So it is somewhere around 0.3. Alpha is approximately 0.3. So concentration of hydroxide ion is now C alpha. C is 0.1, alpha is 0.3. So it is 3 into 10 raised to the power minus 2. So POH is minus log of 3 into 10 raised to the power minus 2. So it is 2 minus log 3. So pH will be 14 minus POH. So 14 minus 2 plus log 3. So it is 12 plus log 3. Log 3 is approximately 0.5. So it is 12.5. That is the way we solve the problems of salt solution. So it is a very exhaustive topic, and in your book Essential Physical Chemistry, all these four categories are described in very detail, and lots of illustrative problems are solved there. A number of different grade problems based on hydrolysis of salts are given at the end of the chapter.